Hi everyone, for this video, we're going to discuss Diophantine equation. Included topics are as follow: linear Diophantine equation, solution of linear Diophantine equation, using Diophantine equation in solving some numerical problems. The objective of the lesson are as follow. At the end of the module, the students are expected to develop an understanding of linear Diophantine equation, be able to identify when a linear Diophantine equation is solvable, be able to determine solutions of solvable linear Diophantine equations, be able to use solutions of linear Diophantine equation in solving certain numerical problem. So what is a linear Diophantine equation? A Diophantine equation is any equation in one or more unknowns that is to be solved in the set of integers. The Diophantine equation in two unknowns of the form ax plus by equals c, where a, b, and c are integers, with a and b not both zero, is called a linear Diophantine equation. A solution of this equation is a pair of integers x0, y0 that satisfy the equation, that is, ax0 plus by0 equals c. Now, here are some famous Diophantine equation. The Pythagorean triple x squared plus y squared equals c squared has actually infinitely many solutions. These are actually sides of a right triangle. Few examples are 3, 4, and 5, since 3 squared plus 4 squared equals 25, which is 5 squared. 5, 12, and 13. 5 squared plus 12 squared equals 13. 7 squared plus 24 squared equals 25 squared. So those are some of the examples of Pythagorean triples. Another famous Diophantine equation is x to the n plus y to the n equals z to the n. Fermat actually claims that the equation for n greater than or equal to 3 has no positive integer solution, but did not provide any proof. It is whilst in 1995 that was able to prove that this theorem is in fact true. Another famous Diophantine equation is the equation of Harvey and Ramanujan. W cubed plus x cubed equals y cubed plus c cubed. The equation actually has infinitely many non-trivial solutions. The smallest non-trivial solution in positive integers is actually given by 12, 1, 9, and 10, since 12 cubed plus 1 cubed is equal to 9 cubed plus 10 cubed. It was famously given as an evident property of 1729, a taxicab number, also named Hardy-Ramanujan number, given by Ramanujan to Hardy while meeting in 1917. So a linear Diophantine equation may have a number of solutions. For example, we have 3x plus 6y equals 18. We can easily see that 3 times 4 plus 6 times 1 is equal to 12 plus 6, which is 18. 3 times 0 plus 6 times 3 is also 18. 3 times 6 plus 6 times 0 is equal to 18. 3 times negative 4, which is negative 12, plus 6 times 5, which is 30, is also 18. So, this particular Diophantine equation actually has infinitely many solutions. And these 4, 1, 0, 3, 6, 0, and negative 4, 5 are just some of them. On the other hand, a linear Diophantine equation may have no solution. For example, the equation 2x plus 4y equals 17 cannot have an integer solution. Why? The left-hand side of the equation is actually always even, because no matter what the value of x, if you multiply it by 2, that becomes even. No matter what the value of y, if you multiply it by 4, that's also even. But the right-hand side is odd. So there can never be a solution for this equation. So how do you find a solution of a linear Diophantine equation? The linear Diophantine equation ax plus by equals c has a solution if and only if d divides c, where d is defined as the GCD of a and b. Now, if we were able to find a particular solution x sub 0, y sub 0, then all other solution may be computed as well using this formula. X is equal to x sub 0 plus b over d times t, and y is equal to y sub 0 minus a over d times t, where t is any arbitrary integer. Let's look at how it works. Find all integer solutions of the linear Diophantine equation 172x plus 20y equals 1000, if it exists, of course. The first thing we need to do is to check if the GCD of A and B divides C, because that's the first requirement of the theorem. That is, if the GCD of 172 and 20 divides 1000. So let's see. 172 is actually 2 times 86. Now, 86 is still divisible by 2, which is equal to 2 times 43. So all in all, 172 is 2 times 2 times 43. On the other hand, 20 is equal to 2 times 10, and 10 can actually be written as 2 times 5. So all in all, 20 is 2 times 2 times 5. We can easily see that the GCD of 172 and 20 is actually 2 times 2, or that's equal to 4. Since 4 divides 1000, the Diophantine equation has infinitely many solutions. So the next step is to find an initial solution. So how do you do this? You use Euclidean algorithm. Of course, you can guess any other solution, but that's only easy to do if the values of A and B are small. If the values of A and B are too large, then trial and error might not be an easy solution. So let's stick with Euclidean algorithm. Let's derive the GCD4. 172 is actually equal to 8 times 20 plus 12. So now we divide 20 by 12. 20 is 1 times 12 plus 8. So now we divide 12 by 8. So 12 is actually 1 times 8 plus 4. So we divide now 8 by 4. Now 8 is 2 times 4 plus 0. Since we already have a 0 remainder, then the last non-zero, which is 4, is the GCD. Of course, we already know it. But we need the Euclidean algorithm so that we may be able to express 4 as linear combination of 172 and 20. So we work our way back starting from 4. So we know that 4 is equal to 12 minus 8. But 8, using the next equation, is 20 minus 12. So we substitute that. 12 minus 1 times 8 is 20 minus 12. So we distribute negative 1 to 20 and negative 12. So we have negative 20 plus 2 times 12. But using the first equation, 12 is equal to 172 minus 8 times 20. So we substitute that here, and we have 2 times 172, and then 2 times negative 8 times 20. Adding that to another 20 here yields 2 times 172 minus 17 times 20. So now, na-express na natin yung core as linear combination ng 172 and 20. We have 4 is equal to 172 times 2 plus 20 times negative 17. So, paano natin ma-achieve yung original equation na 172x plus 20y equals 1000? Note that 4 actually divides 1000. So, what do we need to multiply to 4 so that we get 1000? That's 250. So, that means if we multiply this equation by 250, we get 1000 equals 172, 2 times 250 is 500, plus 20, negative 17 times 250 is negative 4250. So we have the form of the original Diophantine equation, 1000 equals 172x plus 20y. That means we have our initial solution. X equals 500 and y equals negative 4250. So the last thing to do is to use the formula given by the theorem. For other solution, we use x equals x sub 0 plus b over d times t, and y equals y sub 0 minus a over d times t. Again, x sub 0 is 500, y sub 0 is negative 4250, a is 172, b is 20, and d is equal to 40. So we use these values, plug it in here, and we have our solutions. So the solutions are, for x, we have 500 plus 20 divided by 4 times t. So that's 500 plus 5t. For y, we have negative 4250 minus 172 over 4 times t. Or when simplified, that's negative 4250 minus 43t. Of course, for any arbitrary integers t. And that's it. If you want a particular solution, just plug in t here in our two equations, 500 plus 5t and negative 4250 minus 43t for x and y, respectively. Now, if it so happened that the GCD of AB is equal to 1, and since 1 divides any number, then whatever the value of this C in our Diophantine equation, 1 will always divide that. So if the GCD of A and B is equal to 1, then by the previous theorem, this Diophantine equation has a solution. So if you were able to find a solution x0, y0, you just have to plug that in our equation. X is equal to x sub 0 plus b over dt. But now, d is equal to 1. So, you're just left with b. And y equals y sub 0 minus a over d times t. Again, d is equal to 1. So, you're just left with a. So, you have x is equal to x sub 0 plus bt. Y is equal to y sub 0 minus at. Again, for any arbitrary t. That is when the GCD of AB is equal to 1. Let's look at an example. Find all integer solutions of the linear Diophantine equation 5x plus 18y equals 48. We first need to check whether the GCD of AB divides C or if the GCD of AB equals 1. Now, it is easy to see that the GCD of 5 and 18 is equal to 1. So, the Diophantine equation has infinitely many solutions. So, the next step is to determine an initial solution x sub 0, y sub 0. Again, the numbers 5 and 18 are relatively small, so you can just guess any value. For example, I can get y equals 1. So I'm left with 5x equals 30. So I can use x equals 6. So you can use the pair 6, 1 as your initial solution. That's pretty easy because 5 and 18 are small. But if it so happened that these values are large and guessing is hard, you can always use Euclidean algorithm. For the purpose of discussion, let's use Euclidean algorithm. Divide the bigger number 18 by 5 to get the GCD. So 18 is 3 times 5 plus 3. So divide now 5 by 3. 5 is 1 times 3 plus 2. Divide 3 by 2. So you have 3 is equal to 2 plus 1. Finally, divide 2 by 1. So you get 2 equals 2 times 1 plus 0. So the remainder now is 0. Therefore, the GCD is the last non-zero remainder, which is 1. As expected, of course. But the purpose of this Euclidean algorithm is for us to be able to express 1 in terms of 5 and 18. So we work our way from the bottom equation with non-zero remainder and then go up. Starting with 1 equals 3 minus 1 times 2, we get the value of 2 from the second equation. So the second equation gives 2 equals 5 minus 1 times 3. So that's 3 minus 1 times 5 minus 3. Distributing negative 1, we have 3 minus 5 plus 3. So that gives us negative 1 times 5 plus 2 times 3. Again, we get the value of 3 from this time the first equation. So we have 3 equals 18 minus 3 times 5. So we substitute that. We have negative 1 times 5 plus 2 times 18 minus 3 times 5. Distributing 2 gives us 2 times 18 and negative 6 times 5. So we have 2 times 18 minus 7 times 5. 2 times 18 is 36. 7 times 5 is 35. So 36 minus 35 is indeed 1. Again, you don't need to go through the Euclidean algorithm if you can find in any manner that you know values of x and y that will satisfy the equation. For as long as you can get an initial solution, you can proceed to the next step. The next step is using the equation 1 equals 5 times negative 7 plus 18 times 2. We need to express it as the original Diophantine equation, which is 5x plus 18 equals 48. We multiply 1 by 48. So multiply everything by 48, we have 48 equals 5 times negative 7 times 48 is negative 336, and 18 times 2 times 48 is 96. We have an initial solution, negative 336 for x sub 0 and 96 for y sub 0. Now, using this formula, x equals x sub 0 plus bt and y equals y sub 0 minus 80, we get the other solutions. X equals negative 336 plus 18t, y equals 96 minus 5t for any arbitrary integer t. Again, for the Diophantine equation ax plus by equals c, you check first if the GCD of AB divides C. If this is the case, then your Diophantine equation has infinitely many solutions. Get an initial solution. You can guess what the initial solution is, or you can use the Euclidean algorithm. Then once you have the initial solution, use this formula. X equals x sub 0 plus b over dt, and y equals y sub 0 minus a over dt. Special case of this theorem is that if the GCD is 1. So what happens if the GCD is 1? D becomes 1. So your x becomes x sub 0 plus b times d, and your y becomes y sub 0 minus 80. So how do we use the Diophantine equation in solving some numerical problems? Here's an example. Suppose a customer bought a dozen pieces of fruits, apples and oranges, for 132 pesos. If an apple costs 3 pesos more than an orange, and more apples than oranges were purchased, how many pieces of each kind were bought? So always in a word problem, we need to be able to translate in mathematical expression or equations yung mga given. So isa-isahin natin. A customer bought a dozen pieces of fruit. So bumili daw siya ng 12 pieces, halong apples and oranges, for 132 pesos. The cost of the apple is 3 pesos more than the cost of an orange. So mas mahal daw ng 3 pesos yung isang apple kesa sa orange. So kung alam mo yung presyo ng orange, plus 3 yung presyo ng apple. Kung alam mo yung presyo ng apple, minus 3 yung presyo ng orange. So gamit tayo ng variable. Ano ba yung mga unknown? Hindi natin alam kung ilang apple or ilang orange yung binili. Hindi rin natin alam kung magkano yung apple or kung magkano yung orange. So, yun yung mga unknown natin. So, let x be the number of apples bought. Let y be the number of oranges bought. Let c be the cost of an orange. So, c plus 3, the cost of an apple. A customer bought a dozen pieces of fruits. So, anong equation sumukuha natin doon? Yung x plus y equals 12. X is the number of apples plus y is the number of oranges. Should be total to 12. For 132 pesos. So that means whatever the price of an apple, you times that to x. Whatever the price of an orange, you times that to y. The total amount should be 132. So you have 132 equals x times the price of an apple is 6 plus 3, and then y times the price of an orange is z. Now, you can simplify this equation as follow. 132 is xz plus 3x plus yz. Now, if we group every term with z in it, so you have xz plus yz, so you factor out z, so you have x plus yz. But again, x plus y is just 12, so you have 3x plus 12z. So you now have a Diophantine equation, 132 equals 3x plus 12z. Or, since all of the numbers are divisible by 3, you can divide everything by 3 and you're left with 44 equals x plus 4c. So, ibig sabihin, yung problem natin, na-translate natin into finding the solution of the equation 44 equals x plus 4c. This is a Diophantine equation kasi hindi naman pwedeng hindi integer yung bilang ng apples tsaka ng oranges. Kaya, yung mga solution nito, yun yung mga possible solution nung problem natin. So, anong next step? Ang next step is to solve the Diophantine equation. Since GCD ng 1 and 4 is 1, the equation has infinitely many solutions. Again, ano ba yung formula natin pag ang GCD is equal to 1? So, ang formula natin pag ang GCD equals to 1 is i-relate yung 1 in terms of A and B. Now, you don't need to use Euclidean algorithm for this because maliit lang naman yung number. So, hula na lang tayo kung anong kailangan i-multiply sa 1 tsaka sa 4 para pag inad natin yan, may 1. That's easy. Multiply 1 by negative 3, multiply 4 by 1. So, you have negative 3 plus 4 equals 1. Then, from this expression of the GCD, you make it the same as the original Diophantine equation. Sa original Diophantine equation, yung constant natin, 44. So, multiply everything by 44. So, 44 equals 1. Negative 3 times 44 is negative 132. And then, 1 times 44 is 44. So, this is now our initial solution. Negative 132 and 44. So, sabi sa corollary, ano yung formula? Pag meron na tayong initial solution, so that's x equals x sub 0 plus bt and c equals c sub 0 minus 80. Take note, c yung pangalawang variable na ginamit natin. So, wag mo papalito. Kung ano man yung variable dun sa corollary, pwede mo namang palitan ulit yon ng kahit ano pang variable. Basta kailangan mo lang tandaan, yung una, ang formula, initial solution ng una, plus yung bt. B is the coefficient of the second variable. Yung pangalawa, z equals yung unang solution ng pangalawang variable minus yung coefficient ng unang variable. A ang coefficient ng unang variable. Kasi ang Diophantine equation natin ay in terms of x tsaka of c. Okay? So, huwag magpapalit na doon. Pwedeng mapalitan yung variable for as long as you know which stands for x and which stands for y. So, you have the two equations. X equals negative 132 plus 40 and z equals 44 minus t for any arbitrary t. Now, hindi pa tayo tapos kasi ang nasolve lang natin yung Diophantine equation. Pero hindi pa rin natin nasasolve yung original problem. So, gagamitin natin itong Diophantine equation para masolve yung original problem. Analyze natin yung nakuha nating solution ng Diophantine equation. Analyze natin yung Diophantine equation. Yung x is the number of apples bought. For any arbitrary integer, yung x at yung c has infinitely many solution. Pero hindi lahat ng value ng t, may sense yung makukuha nating solution dun sa original problem. Yes, it will satisfy the Diophantine equation, but the result may not be sensible. Bakit? Halimbawa, yung t na kukunin natin ay 1. So, yung lalabas na value ng x, negative. Eh, hindi naman tayo pwedeng bumili ng negative na apples. Anong ibig sabihin nun? Kung lalakihan natin yung 4t, sabihin natin yung t, gawin natin 100. So, magiging this value becomes 4 times 100. That's 400. Negative 132 plus 400. Sobrang dami namang apples nun. Eh sabi natin, 12 lang yung total number of orange and apples na binili. So, ibig sabihin, hindi lahat ng value ng t magbibigay ng sensible scenario dun sa original problem. So, again, kung i-analyze natin yung solutions na nakukuha sa Diophantine equation, hindi lahat ng value ng t magbibigay ng sensible solution sa original problem. Yun lang mga values ng t kung saan ang makukompute nating x ay between 6 to 12 ang pwede nating i-consider. Well, ano bang ibig sabihin para ang x maging between 6 to 12? Yung value ng x natin is negative 132 plus 40. So, gusto natin between 6 to 12 lang siya. Hindi pwedeng equal sa 6 kasi gusto natin mas marami yung apples kaysa sa oranges. So, dapat mas malaki sa 6. Pwedeng mag-equal sa 12. Pero ang ibig sabihin, pag ang apple naging equal sa 12, wala kang orange na binili. Kung isosolve natin yung inequality na to, add 132, add 132, add 132, so we have 138 is less than 40 and 40 is less than 144. So divide everything by 4 gives us t is between 34.5 and 36. Siyempre, hindi pwedeng 34.5. So, ang pwede lang value ng t ay 35 and 36. Kung gagamitin natin yung value ng t na to, makukuha natin ang x equals negative 132 plus 4t. So, that gives us, when t equals 35, x equals 8. Y equals 12 minus 4, so that's y equals 4. Now, kung 36 naman ang gagamitin nating value ng t, so makukuha nating x ay negative 132 plus 4 times t, so that gives us 12. So, kung 12 yung apples mo, edi wala kang orange. Kung pag-aagrihan natin na parehong bumili siya ng apple and oranges, then yung solution na t equals 35 yung gagamitin natin. That means, bumili siya ng 8 apples for 12 pesos each and 4 oranges for 9 pesos each. Pero, kung hindi natin ililimit sa condition na kailangan parehong apple at orange yung binili, pwede rin na bumili siya ng 12 apples at 11 pesos each, tapos hindi siya bumili ng orange. Lahat ng diniscuss natin can also be found in the following reference material: Barton Elementary Number Theory, Ireland and Rosend, A Classical Introduction to Modern Number Theory, Cauchy Elementary Number Theory with Applications, and Niven, Zuckerman, and Montgomery, An Introduction to the Theory of Numbers. That's it, guys! So sana nakatulong to for you to understand solving linear Diophantine equation. See you next time!